Today we're going to discuss section 12.8 and 12.9, which involves molecular structure. So molecular structure is the 3D arrangement of atoms in a molecule. So far we've looked at Lewis structure, which is just a two-dimensional arrangement, but that's not how molecules occur in nature. So we're going to look at their 3D arrangement. We're going to use bond angles to do this, and some types of shapes include bent, linear, trigonal, planar, and tetrahedral. So we're going to look at what's called the VSEPR model. This is a structure, a way to determine the structure, because structure helps determine the properties of the molecule. And we'll talk more about that once we talk about how to determine structure. So VSEPR is a system for predicting molecular structures. Just like we have a way of naming all of our compounds, the IUPAC system, we have a system for predicting structure. VSEPR stands for valence shell electron pair repulsion, and that's because molecules want a structure that minimizes the repulsion between the electron pairs. So basically, electron pairs want to be as far away from each other as possible. And so based on the Lewis structure, we find a way to do that. And so we're going to put bonding and non-bonding pairs as far apart as possible. So let's look at some steps for predicting molecular structure. First thing you have to do is draw the Lewis structure. So we've already talked about how to do that. Then you're going to count the number of lone pairs and the number of bonded pairs around just the central atom. Okay, so it's all about locating that central atom and then looking at lone pairs and bonded pairs. We're going to count double and triple bonds just like we would a single bond, so they're going to count as one bonding site. And that's because even though it's a double or a triple bond, it counts as one repulsive unit, and so it's one bonding site. And then we have a chart that we're going to use to figure out the shape, or you basically just want to arrange those bonding sites as far apart from each other as possible. So here's the chart that we're going to use. This is the total number of bonding sites, and then over here we have the number of lone pairs within that those bonding sites. And you can see we've got lots of different shapes and structures, and so we'll look at some of those, the most common ones. Okay, so let's look at NH3. So the first thing that we need to do is draw the Lewis structure. Well, I know that nitrogen is going to donate 5 valence electrons. Remember, that's coming from the group number. And each hydrogen donates 1, but there's 3 of them. So this gives me a total of 8 valence electrons. Well, there's only one nitrogen, so I'm going to call that our central atom. I'm going to bond 3 of the hydrogen on 3 of the bonding sites. And then before I even look at how many I have available, I'm going to make sure everything is stable. And so each hydrogen has 2 electrons or 1 bond, so that satisfies the duet rule. And nitrogen has 2, 4, 6, 8, and that satisfies the octet rule. And so I've used 8 and I had 8 available. So first step, Lewis structure, done. Now I want to look at my central atom. So I'm just going to draw a box around it. Okay, within the central atom, I have 1, 2, 3, 4 total bonding sites. And within those 4 bonding sites, one of them is a lone pair. And so if I'm looking at my chart, I'm going to go down to 4 bonding sites, 1 lone pair, and that gives me this shape right here, which is trigonal. It says pyramid, but we're going to say pyramidal. And so then if I redraw my my structure, let's erase. Let me erase. If I redraw my structure using this geometry, I've got nitrogen, my lone pair on top, and then do you see how we've got open triangles, squiggly triangles, and straight lines? Straight lines mean that it's in the plane. So like with the screen, empty triangle means it's sticking out of the plane, so like sticking out at you. And then the squiggly triangle means that it's sticking into the plane or into the screen, so sticking back. We're going to do some work with 3D structures because I always have a hard time visualizing this. But basically you've got like a triangle-shaped pyramid on the bottom with the nitrogen on top. Okay, let's look at a different one, which is CH4. So I know carbon is going to donate 4 valence electrons. Each hydrogen donates 1, but there's 4 of them, so this gives me a total of 8. Carbon is going to be my central atom, and because I have 4 hydrogens, I'm going to put 1 in each bonding site. So now I've satisfied the duet rule for hydrogen, and I've satisfied the octet rule for carbon. So I've used 2, 4, 6, 8, and I had 8 to start with, so I'm all set with my Lewis structure. So now, if I draw a box around my central atom, I have 1, 2, 3, 4 bonding sites and 0 lone pairs. So I'm going to go to 4 bonding sites, but this time I have no lone pairs, and so that means I'm here, and this one is tetrahedral. And so if I draw that, I've got my carbon in the center, I have a hydrogen in the plane here, and a hydrogen in the plane up here. I have one sticking out of the plane, and I have one sticking back into the plane. Okay, so whereas with NH3 this was a lone pair, now it's a hydrogen, so we have a different shape because we're going to have different repulsion if it's an element versus a lone pair. Okay, let's look at one more example. Let's look at water. Okay, so hydrogen donates 1 valence electron, but there's 2 of them. Oxygen donates 6 valence electrons. And so again, we have 8. That's really common this time. Oxygen is our central atom. Bond our hydrogens. Make sure oxygen's octet rule is satisfied. So now I've got 2, 4, 6, 8. And I had 8, so I'm all set with my Lewis structure. If I draw a box around my central atom, I have 4 total bonding sites. 2 are bonded pairs. 2 are lone pairs. So that means I have 2 lone pairs. So now I'm going to go down to my 4 bonding sites again, but now I'm going to 2 lone pairs, and so that gives me this shape, which is bent. And so my central oxygen is going to go here. I've got a hydrogen in the plane on the left, a hydrogen in the plane on the right, and then my lone pairs are up at the top at angles because I'm trying to get them as far apart from each other as possible. So what happens is that these lone pairs take up so much room that they push those hydrogens down, and so that's why we have this bent structure. So that's basically it. So here are some problems to work on, and we'll discuss this more in class. Have a good day.